Today we are going to learn about implementing hyperparameter tuning with MLflow. We'll cover practical techniques to automate and track hyperparameter experiments using MLflow, enhancing your machine learning model's performance. Hyperparameter tuning is a crucial step in the machine learning workflow. It involves selecting the best set of hyperparameters for a learning algorithm. These parameters control the learning process and affect the performance of the model. Common hyperparameters include learning rate, number of epochs, and batch size. The challenge lies in the fact that there is no analytical solution to determine the best hyperparameters, and it often requires a combination of experience and experimentation. This is where MLflow comes into play. MLflow is an open-source platform that helps manage the machine learning lifecycle, including experimentation, reproducibility, and deployment. Today, we'll explore how MLflow can assist in hyperparameter tuning and optimize your model's performance.
To get started with MLflow, first, you need to install it. You can do this with a simple pip command, pip install MLflow. Once installed, you can create an MLflow project by organizing your code and data in a structured way. MLflow projects are self-contained units that encapsulate your ML code and environment. You can track experiments by setting up an experiment in MLflow, which allows you to log parameters, metrics, and artifacts. This is crucial for comparing different runs and understanding what changes lead to improvements. The MLflow UI provides a visual interface to view and compare experiments, making it easier to analyze results. Tracking experiments not only helps in keeping a record of your work but also aids in reproducibility and collaboration. With MLflow, you can ensure that every step of your model development is documented and accessible for future reference. A search space is a range of values that hyperparameters can take. Defining an appropriate search space is vital for effective hyperparameter tuning. There are several types of search spaces, including discrete, continuous, and categorical. In MLflow, you can define search spaces using libraries like Hyperopt or Optuna, which MLflow integrates with seamlessly. When defining a search space, consider the range and type of each hyperparameter. For instance, a learning rate might be continuous, ranging from 0.001 to 0.1, while the number of layers in a neural network might be a discrete integer. A well-defined search space can significantly impact the efficiency of the tuning process, as it reduces the time and resources spent on evaluating less promising hyperparameter combinations. By setting clear boundaries and types for each parameter, you guide the search process towards more promising areas of the hyperparameter landscape.
Grid search is one of the simplest methods for hyperparameter tuning. It involves exhaustively searching through a specified hyperparameter space to find the optimal set of parameters. In MLflow, you can implement grid search by defining a grid of hyperparameter combinations and using MLflow to log each run with different parameter settings. The main advantage of grid search is its simplicity and thoroughness, ensuring that every possible combination is evaluated. However, it can be computationally expensive, especially for large search spaces. An example of grid search could involve tuning the learning rate and batch size for a neural network. By systematically evaluating all combinations, you can identify the best settings for your model. While grid search is exhaustive, it might not be practical for complex models with numerous hyperparameters. Nonetheless, it's a good starting point for smaller models or when computational resources are not a constraint. Random search is a more efficient alternative to grid search. Instead of evaluating every possible combination, random search samples a fixed number of hyperparameter combinations from the defined search space. In MLflow, you can implement random search using libraries like scikit-learn or Optuna, which integrate with MLflow for logging and tracking. The main advantage of random search is its ability to explore a wider range of hyperparameter configurations with fewer evaluations. This makes it less computationally expensive than grid search while still being effective in finding good hyperparameter settings. An example of random search could involve tuning hyperparameters for a decision tree classifier. By randomly sampling different combinations, you may discover optimal settings that grid search might overlook due to its structured approach. However, random search does not guarantee finding the absolute best combination, especially if the search space is vast. Nonetheless, it offers a balance between exploration and computational efficiency.
One of MLflow's core functionalities is experiment tracking, which involves logging parameters, metrics, and artifacts for each run. By using MLflow's tracking API, you can log hyperparameter values, evaluation metrics like accuracy or loss, and any artifacts such as model files. This allows you to maintain a comprehensive record of each experiment. Once logged, MLflow's UI enables you to compare different runs visually, making it easier to identify trends and evaluate the impact of hyperparameter changes. For instance, by comparing accuracy metrics across runs, you can quickly spot which hyperparameter settings yield better performance. Logging experiments with MLflow not only aids in analysis but also enhances reproducibility. You can revisit past experiments, replicate conditions, and build upon previous work without starting from scratch. This systematic approach to logging and comparison is invaluable for both individual practitioners and teams working collaboratively on machine learning projects. The MLflow UI is a powerful tool for visualizing experiment outcomes. Upon logging your experiments, you can navigate the UI to view metrics, parameters, and artifacts associated with each run. The UI provides a clear and organized way to evaluate the performance of different hyperparameter settings. You can create custom visualizations to analyze trends and patterns, such as plotting accuracy over time or comparing the impact of different learning rates. These visual insights are crucial for understanding the behavior of your model and making informed decisions. Furthermore, MLflow allows you to export visual data, enabling you to share insights with stakeholders or include them in reports and presentations. By leveraging the MLflow UI, you can transform raw data into actionable insights, enhancing your ability to tune and optimize hyperparameters effectively. To maximize the efficiency of hyperparameter tuning, MLflow can be integrated with popular libraries like Hyperop, UpTuna, and scikit-learn. These libraries provide advanced tuning algorithms, including Bayesian optimization and tree-structured parser estimators, which can be automated and tracked using MLflow. The integration allows you to log hyperparameter trials, metrics, and outcomes seamlessly, leveraging MLflow's tracking and UI capabilities. This automation reduces manual effort and enhances reproducibility, as all tuning processes are documented and accessible. For instance, using UpTuna's sampler with MLflow logging enables you to explore complex search spaces efficiently while maintaining a comprehensive record of each trial. By integrating MLflow with these libraries, you streamline the tuning process, making it more efficient and scalable, especially for large-scale machine learning projects.
Once you have conducted hyperparameter tuning experiments, the next step is analyzing the results to select the best configuration. Using MLflow's comparison tools, you can evaluate different runs based on metrics like accuracy, precision, recall, or any other relevant measure. The goal is to identify the hyperparameter settings that optimize model performance while considering trade-offs such as overfitting or training time. For instance, a model with high accuracy but long training time may not be ideal if deployment speed is a priority. By analyzing the results logged in MLflow, you can make informed decisions and select the final hyperparameter configuration that aligns with your project's objectives. This process not only improves the model's performance but also ensures that the selected configuration is well documented and reproducible for future use.
In conclusion, hyperparameter tuning is an essential part of the machine learning process, significantly impacting model performance. By utilizing MLflow, you can automate and track this process, making it more efficient and reproducible. We covered key concepts such as setting up MLflow, defining search spaces, and implementing grid and random searches. Integrating MLflow with tuning libraries further enhances the tuning process, allowing for more sophisticated exploration of hyperparameter configurations. As you move forward, I encourage you to experiment with these techniques in your projects, leveraging MLflow's capabilities to achieve optimal results. Thank you for joining us in learning how to implement hyperparameter tuning with MLflow.